Right, today then, just to finish these last two slides, I just didn't do them last day. So solution methodology. I'm not going to make it full screen. It's going to take a minute. So this is just to mention one other option you have in Fluent and the same in OpenFOAM or any CFD solver. That when you're setting up a fluid simulation, you will have this pressure velocity coupling. So most of these simulations we're looking at for incompressible CFD, the unknowns are pressure and velocity. So for every cell, there is an unknown pressure and an unknown velocity vector. That's what it's trying to solve. So we have our Navier-Stokes equations applied to each, discretized and applied to each cell, and we're trying to calculate those big set of simultaneous equations. So there's various ways you can write a procedure to solve those equations. And engineers love coming up with acronyms or backronyms. So there's simple, simplex, iso, coupled, and then there's some other ones in OpenFOAM as well, simple. So all of these engineers just think it's a great idea to make it line up with a real word. So the actual acronym doesn't make perfect sense. But anyway, here's just some guidance I have on these slides for why you might pick one rather than the other. So simple and simplex. Actually, before I give you the details, if it converges, you get an answer, the residuals converge, all of these will give you the same answer within some particular iteration error. So it doesn't really matter. So why we choose one is just, it might be faster, it might be more efficient in terms of resources, the amount of RAM you have in your computer, and it might be more robust. By robust, I mean for changing certain parameters, velocities, and I press go, I still get an answer. So from that perspective, this coupled approach, that tries to solve the, say, the 4 unknown equations for all cells at the same time. That's what it means by coupled. So that makes a very large linear system because it's solving all 4 equations for all cells at the same time. That tends to use more RAM. So if you have millions of cells, you might not have enough RAM on your computer. But it tends to be the most robust, as in you can have a kind of bad mesh, change the boundary conditions a lot, and it can still work. So coupled, I think, is probably the default now. And normally that's fine. But sometimes for transient, piezo can be more efficient, or simple simplex can be more efficient for steady state. So if it's a transient problem, piezo might be faster if your time steps are small, whereas a steady state, simple might be faster. Generally, coupled is pretty good though. Without going into the details of piezo and simple, the general idea is they just maybe solve the momentum equations holding the pressure equation constant, and then they flip and solve the other one. So they don't solve the full system at the same time. They solve a little bit, then the other bit, and they do some tricks to iterate between them. So they use less RAM, and much less RAM than a couple of others. Most computers have a lot of RAM now, particularly supercomputers, so it's less of a challenge. Okay, before I go on to turbulence modeling, which will be the main focus of this lecture, I just wanted to show you something on Taylor series. So when I went through the finite volume method, when I was doing a volume integral, or a surface integral, I took the unknown thing and I replaced it with a truncated Taylor series. And I didn't really tell you anything about that. So what is that? I go down here. So this expression here, or this one here, even, both of them are fairly similar, basically says if I want to approximate the value of a function, some maybe complex function at a point, I can write the value of that function as a sum of many terms called a Taylor series. If I write out all the terms, that fully describes the function. You can rewrite the function in a Taylor series. So most functions can be, like polynomials, can be written as a Taylor series. But a truncated Taylor series means you just don't go to infinity, you truncate it. So you're like, if I have enough terms, 3 terms, that might be good enough for what I need. So we use the truncated series. So the idea is, by some function, I can say that function within some region of x is just equal to the value of a. So a is just some point in x. So a particular coordinate that we're interested in approximating the function. So let's say this is 0. So this is, for example, here they just sub in the coordinate 0. So let's say I'm trying to approximate this function around x equals 0. I can say, well, that function is equal to the value at 0. This is the derivative. So differentiate with respect to n x1s, divided by 1 factorial, so it's 1, plus the second derivative, so at that point 0, divided by 2 factorial, x squared, and then you keep adding on these higher and higher derivatives. So what that lets you do is, for some function in some region, you can just write that entirely in terms of the value at one point and the derivatives at that point. So if you only know values at one point and the derivatives at one point, you can approximate the function away from that. That's the idea. So that maybe is a little bit abstract. So I found there's actually a nice interactive tool, desmos.com calculator. This is an interactive tool. I'll put a link for this for a Taylor series. So how does this work? So let's say we have a function. Let's say it's sine x. So sine x is this bit. And let's say in the region of 0, so I can set a equals 0. I can set it to a different point, but it works the same at any point. So let's say I'm at x equals 0. So that's my a equals 0. And this blue curve is only my Taylor series. So let's go to my Taylor series. N here represents how many terms I have. So if I have 0 terms, that just means the constant, just f equals 0. So this is a truncated Taylor series where I just have one term. So this purple line is basically just saying, around this point here, I can approximate the value of this function by just taking the value at that point. Okay, so that's not a great approximation. So let's add it to one term, so the first derivative term. There we go. Okay. So now, using the value at that point and the gradient at that point, I can approximate this sine curve in the region of this point using the value and the slope. So you can see, actually, in this region here, that's actually probably an okay approximation. And that's essentially what we're doing in the final value method. If we have enough cells, then you can see that's actually fine. If we have enough cells across the sine curve, that's actually fine. And as long as we're in the asymptotic region, it's fine. But you can see if we added a quadratic term, oh, it's the same because it doesn't matter. Oh yeah, because it's 0 is the quadratic. Thank you. So if you had the quadratic term, it actually doesn't make. If you had the cubic term, there. All right. Okay. So if you had the cubic term, you can see, okay, you can expand the region where we get a good approximation, but then far away, it's terrible. So what we're doing here is only using the value of the function and its derivatives at that point to approximate away from them. So the more derivatives we are, the further away from that region. And that's the kind of basis of this truncated series. So for example, if I start going up to 5, 6, 7, 8, 9, so you can see, okay, away from it. If you keep adding terms, you get further and further away. And if you add an infinite number of terms, you can describe the function fully. That's the idea. So Taylor series and truncated ones generally can work well, particularly for polynomials and most standard functions, but they actually don't work for all functions. So for example, if I could define a function that is just equal to 2 here and equal to -2 here and has a discontinuity. So if there's discontinuity, then the derivative doesn't really give you any information across the discontinuity. So then there's a field in finite element, finite volume. If you have shock waves which are discontinuous, then that causes problems where these things break down. I'll put a link to that. Okay, so that's essentially what we were doing, this truncated Taylor series. That's just what I meant by it. So this Taylor series or truncated Taylor series tends to appear in numerical methods as a way to estimate accuracy and are to be used. And if the coordinate you're writing the Taylor series away from is 0, that's just called a Maclaurin series. So a Maclaurin series is just a Taylor series where the A is equal to 0. If it's not 0, it's just a Taylor series. So they're all these related series. Very good. All right, so then for this lecture, I'm going to talk about turbulence modeling. So this will be relevant to the assignment and then the lab this week. I think this. What is turbulence? You already have an idea what it is. At a very basic level, it's a population of many different eddies or vortices. So these are regions of rotating, and there are different sizes and strengths and velocities. So a collection of little ones and big ones. And they're embedded in each other, and they're forever changing in a random or chaotic fashion. So if at some location, for example, in the flow, I were to measure maybe the velocity, if I had this kind of random variations or chaotic variations in velocity that was indicative of turbulence. And you could look at the same for other field quantities like pressure or water stress or things like that. So they tend to change continuously in time, and they have a random or chaotic behavior. So it's not that they're repeating. So for example, in the vortex shedding assignment, I think last week or the lab, that's laminar. You can have vortices that are kind of repeating and they follow a particular pattern. That's laminar. But if it's chaotic, then it's perfect. So in turbulent flow, the size of the largest vortex or region or eddy or region of rotating fluid, that's set by the geometry. So that's not set by the flow or the properties of the fluid. It's not set by the velocity. It's set just by the geometry. So for example, if I flow through a pipe, the largest possible eddy I can get into that pipe will be the diameter of the pipe, right? So it's just dictated, in the internal flow, it's just dictated by how big an eddy I can fit in. For external flow around something, the size of the biggest eddy tends to be about the size of the thing you're flowing around. So the biggest region of rotation around an airplane is about the size of the airplane. Some, like approximate. So like this eddy here might be about the size of the wingspan or something like that. That's the biggest possible one. So the largest eddy is just dictated by geometry, whether it's the geometry flowing around or the geometry flowing through. But the size of the smallest eddy is set by the Reynolds number. So the higher the Reynolds number, the smaller eddy, the smallest eddy becomes. The largest one is just dictated by the geometry. The smallest one is by this Reynolds number. So if Reynolds number can be interpreted in multiple ways, we can think of it as a ratio of this inertial forces to viscous forces. And that's the way it was derived. But you can also think of it as an indication of the range of scales of the flow. So a large Reynolds number means that the ratio of the big eddies to the little eddies is very large. If you have a very low Reynolds number, then the eddies are all about the same size. Okay. So at the largest scale, when you have these large rotating pieces of fluid, these eddies or vortices, they have a lot of inertial energy and they're rotating. And viscous effects at that scale tend to be small. So the effect of viscosity, this friction between the gas or the water or liquid, this dissipation of energy, that tends to be small for the large eddies. So what happens is the energy in this rotation, this vortex, tends to split into smaller ones. So its energy gets broken up into smaller vortices. Then those ones break up into smaller ones again, and those ones break up into smaller ones again, and every time they're breaking it and they're dissipating it. Once you get to the very smallest scale, then for those rotations, then the viscous effects become important. And then the energy of this kinetic energy of rotation just dissipates into heat. So just from friction, all the particles rubbing off each other. So eventually your energy goes in from your airplane here, generates a big vortex, that spins around, makes littler vortices, which make littler ones, which make littler ones, each dissipating a little bit of energy. But the smaller you go, the more energy is dissipated. And then at some point they get so small that viscosity just dissipates and you don't get anything smaller. So the Reynolds number, another interpretation is it gives an indication of the scale at which this viscous dissipation happens. So the higher the Reynolds number, the smaller these small eddies are, where they dissipate and turn into heat. So turbulence, and you could spend a course on turbulence, but that can be represented as an energy cascade. So on the x-axis here, this is the diameter of the rotating eddies. So D max, these are big rotating eddies, and these are small. And this is their velocity. So we have some large eddies here with a large velocity, and you can't have any ones larger than that because your pipe can't have a bigger eddy, or your airplane can't make a bigger eddy. So the largest one is just dictated by the geometry. Those large eddies will split into smaller eddies. That gets lower and slower and slower, or have lower orbital velocities or rotational velocities. And then at some point, we get to this minimum level where this effects dominate and it just dissipates the energy of these little rotating eddies, and it just aren't used. And so you can't have eddies smaller than that. They just won't sustain themselves. They'll just dissipate this viscosity. So there's a minimum physical spatial scale and a velocity minimum scale as well. So these small scales we can actually approximate. So this guy Kolmogorov came up with these expressions where you can actually calculate the minimum diameter and the minimum time it takes to rotate. So that's maybe you can convert that to velocity. But this you can represent as like the period of rotation of one of these. So you can calculate that in terms of the Reynolds number. But remember, the Reynolds number is just a function of density and viscosity, or kinematic viscosity, and your far field velocity and some reference scale. So you can approximate the size of this smallest diameter. So you can see it's a function of your viscosity and the length and the velocity. So the higher your velocity, the smaller this will be, because like your Reynolds numbers increase. But the higher the viscosity, the bigger it gets. So if you have more viscous fluid, you can't have really tiny eddies. So like in honey, it'd be very difficult to drive very tiny eddies in. So for example, if I give you these formulas and I show you here's a Prius, and I say, well, what are the scales of the smallest eddies created in the wake of a car driving at typical cruising speeds? So I'm not going to get you to calculate this now. I assume you can use the formula. But I plugged in the numbers and you can double check this. So if you assume it's driving 100 kilometers per hour, that's around 30 meters per second. And you can double check this. If you plug that in, the kinematic viscosity there is 2e to the minus 5. That's 30 meters per second squared. The length of my car might be 2 meters approximately. Like this is an approximation. It doesn't have to be exact. Get the quarter root of it. So that will come out of the order of maybe 10 microns or something like that. So it means if your car is driving along, you'll have big eddies the size of 2 meters that you can maybe see in the smoke, or maybe you can't if you have a Prius, which is running hybrid. But if you have a normal internal combustion engines. And so you see those, but they'll be splitting the smaller ones. But the smallest ones will go to 10 microns. So for reference, human hair, I think, is it 50, 100 microns or something like that. Carbon fibers are about 10 microns. But like these are really small. So the smallest eddies are really, really, really small. Okay. And their frequency to reach, they're rotating probably every 10 microseconds as well. So they're really small, fast rotations. Okay, so that's a little bit about turbulence and understanding what's happening when you have turbulence. So what do we care about? We care about how do we model it. So now that we understand that at least at a high level, how it works, how can we model it? And there's 3 classic ways to model turbulence of increasing accuracy and decreasing cost. So the first method we're going to talk about is called DNS, or direct numerical simulation. And this is a 2D direct numerical simulation. And before I go through any of the points, just looking at this, you can see this is a very high resolution data set. This is a model that has very, very fine cells. And it really is capturing all these tiny, tiny little eddies. You'll see the largest possible eddy is about the size of the diameter of the box. So you can see some of these large rotations about the size of the box approximately. And they're splitting into, if you zoom in very close, they're orders of magnitude smaller. So what is DNS? DNS is just take the Navier-Stokes equations, and in practice, it would mean just use a fine enough mesh and a fine enough time step to describe all the eddies. And that's it. So the Navier-Stokes equations fully describe turbulence. So sometimes there's misleading quotes about turbulence, where people say turbulence is not mathematically understood, etc. There's lots of things at a high level that maybe it's difficult to predict, but the actual mathematical equations, Navier-Stokes equations, fully describe turbulence deterministically. They're very sensitive to initial conditions. But the Navier-Stokes equations, if we open up fluid, calculate the Kolmogorov scales, and make our mesh fine enough, and our time step fine enough, it will describe all of that. There's some practical concerns. You'll have billions of cells, etc., but that will work. So DNS, or direct numerical simulation, it means that you resolve spatially and in time, you resolve the finest eddies. So make your mesh finer than the smallest possible eddy, and then you will capture all of this information, and that's what you're doing. And so all the motions contained in the flow are resolved, and by resolved, I mean we make a mesh fine enough, and we make sure that we have a mesh that's finer than this d-min, and a time step finer than this t-min, to capture all the information. So that's DNS. clearly, this is going to be super expensive. So even for this 2D case here, it's probably run on a supercomputer for on many hundreds, if not thousands of cores. Even the results coming out of this, if you have 100 million cells, when it saves a time step, it'll probably be like a 50 gigabyte file just for one time step. So just the practicality of that for designing a car, it's not very practical. Never mind how long it will take. So this is the most expensive, but the most accurate way to deal with turbulence. So that's DNS. For reference, this is a slide from a keynote. I was at a conference last year in Italy, and it was an open phone conference. And there was a keynote from a guy in Amazon Cloud Computing, and Neil Ashton. He's an English guy, but he kind of runs their CFD division. So a lot of companies now will use cloud to do simulations. So he said he did a calculation for how much it would cost to do a DNS simulation of an aircraft taking off. So he said, never mind if the software doesn't exist, the theory exists, and there are some high-end parallelized codes that in theory maybe could get to that. And so he said, you'll probably need NC's number of cells, about 10 billion cells. And your time steps, you'll probably need about 40 million if you want to simulate 4 seconds for a high-lift situation, which is not very long. And your time step, you'll need to have about a tenth of a microsecond. Okay? So he said the number of cores, CPU cores. So if we use 333,000 CPU cores, it would take about 23 days based on current technologies, current softwares. So with current best costs out there for Amazon, that's about $5 million just to run that one simulation. And he said, oh, okay, new next generation codes are going towards GPUs. Maybe we can, in the next year or two with GPUs, we could get it down to like 1,000, just over 1,000 really high-end GPUs, and then we might get it down to 3 million. But it's not going to be 100,000. It's going to be like billions. So in practice, that we're maybe 10 years ago, DNS was not something that could be used in engineering. It was just a scientific toy to play with to understand the fundamentals of turbulence in a box. But now, essentially, Moore's law, things are exponential. We're approaching it. So maybe in 10 years, DNS will be used for things like that. But at the moment, it's incredibly expensive. If you were to do wind tunnel tests for some of these aircrafts, they're super expensive as well. So, but at least maybe there's less uncertainty. But that's just to give you an idea of where it is at the moment, or at least last year. But this is a still rapidly changing, accelerating field as new softwares are developed. So that's DNS. You're probably not going to be yes, a question. I think this is the first question we've had. Thank you. Why would you use DNS? So, for example, if it's not too expensive and you really want to understand the turbulence, then great. But if I'm saying that maybe that's not practical, it lets you describe turbulence very precisely. So when we go to the other methods, which don't describe turbulence precisely, they have to be calibrated or tuned to give reasonable results. So what do we tune them against? We can tune them against experiments, and that's what you do, but you can tune them against DNS models. So DNS is used to design or tune what are called turbulence models. So we haven't talked about turbulence models. So to tune practical approaches to do calculations with turbulence, basically, in practical amounts of time. That's one way. Other places is people just fundamentally want to understand what happens. Let's say if I have heat effects and then turbulence, or like multiple phases like water and air mixing under certain scenarios. Fundamentally, how does energy go from this part to this part? And then people can kind of do fundamental studies of how energy is transferred in turbulent systems and come up with new physical principles based on what they've seen in that. So that they're kind of two reasons you might do it. Or maybe you want to show off. Or actually, maybe a new high performance system, you might want to benchmark it. You need an expensive model to benchmark it on. So yeah, but maybe the practical reason is you might use it to tune later models. So if DNS is the most expensive, it's not really practical at the moment. LES is something that is practical. We're not going to even do LES because it's expensive. We're going to do the next level up, but it's useful to understand. So what is LES? Large eddy simulation. So if I were to look at velocity at some point in my flow, the true velocity might have all this random noise and it's going up and down like this, and it has like a low frequency randomness, but also high frequency. So if I did DNS, I just capture it. LES is, okay, if we can capture the big turbulent eddies, that will give us most information, and all the little ones are less important. So large eddy simulation, it means you just you resolve the large eddies. And by resolve, I mean you make a mesh fine enough to get all the large eddies, but not fine enough to capture all the really small ones where energy is dissipated. So for those small scale ones, they say they're approximated or modeled. So I know this might be a bit confusing, like modeled. Modeled normally we mean by mathematically modeled, or to put it a different way, they write a mathematical equation that describes the effect of those really small eddies on the macroscopic flow. That's the idea. So you have these what are called subgrid scale models. So you have a mesh that's fine enough to get the big eddies, and then for all the eddies smaller than that, you write a maths term that you add into your Navier-Stokes equations that tries to mimic their effect. And how do you come up with those maths equations, or how do you tune them? DNS is one way to do that, but there might be other ways to do it as well. So LES is far less expensive than DNS, but it's still very expensive relative to RANS, and RANS is the third approach we're going to look at. RANS is what you're going to use in the lab. So it's often too expensive for engineering flows, but actually it's so I probably started teaching this course 10 years ago, and it's actually changing now. So now you see commonly at conferences, even industry people using LES for designing things. So I think I have, yeah. So Upstream CFD is a consultancy company that do CFD. So they work very much in the automotive sector, and I saw them present this at a conference. So this is an LES or something like an LES of maybe an Audi, I guess. It looks like Audi. So this is an LES. So if you look at this, the mesh is not 10 microns, but it's definitely millimeter scale. So this will already have probably 100 million cells in it. But you can imagine this will give very precise lift and drag. Car companies care about dropping the drag and things like that, fuel efficiency, things like that, etc. So maybe they can play with changing the shape of this and run this. Still, your average Audi engineer is not firing out an LES simulation every day. This is something where they have a specialized team that will come in and do it. But the RAN simulations is something they could do every day. So these are also very large data sets as well. So this would be LES. So the last one, the highest level, if there's kind of DNS is one bound of super accurate, very expensive. RANS is less accurate, but very cheap. And then LES is somewhere in between. So RANS or Reynolds are sometimes called RAS or ES. So Reynolds average Navier-Stokes. So if the flow is statistically steady, we can average the equations over time or over an ensemble, and I'll explain what that means. So this is flow over a backward facing step. This is a canonical test case for fluid mechanics. You have turbulent flow coming over, you get all this noise. If we did a video, this would be shaking like mad in time. But we can just take the average in time, like experimentally, we could define the average at every point in time, and that would give us a flow that looks like this. So the idea with RANS is, let's not worry about the random variations in time. Let's just try to calculate the mean flow. So for example, over a car, I'll just calculate the mean drag. I don't care about the actual drag, how it varies every microsecond. I just want the mean flow, the mean drag, and that will let me design things. So that's a practical approach, okay? So RANS gives you mean quantities. And by mean, we can consider it to be time average, or another perspective is what's called ensemble average. So imagine you did 1,000 experiments that are all the same. You do wind tunnel downstairs, and then you just say after 100 seconds, I will measure the drag at that exact moment. And then you do that with 100 experiments. So you get some random variation between all of them, and you'll just define the mean across all your experiments. So an ensemble is a bunch of experiments. So you can define the average across experiments that varies in time as well. So you could have 100 experiments and just take the average in time, and that will have a time varying curve that's smooth. It's the average, across the ensemble. So there's just two perspectives. So RANS is pretty cheap. You can do RANS of a full car 3D. You can probably do it on your laptop in an hour, something like that. It doesn't need super high resolution, so it's very practical. Other turbulence modeling approaches, and this is a giant field of research. There's people who just do their PhDs on turbulence models coming up with a slight variation. But because the gap between RANS and LES is still large, so if you go from a RANS simulation with a steady state, just one time step, to LES, which needs a finer mesh and needs 1,000 time steps, you're still talking about orders of magnitude computational jump from RANS to LES. Never mind units. So people have come up with all these. Once again, it's almost like a continuum of approaches. So you can have unsteady RANS, DES, DDES, VLES. There's all these engineers come up with amazing names again. So VLES, very large eddy. So you can imagine They just defined a limit somewhere before. So it's a real scientific error. But DES is probably one of the most common variants of DES. So DES is kind of a blend between RANS and LES. It's RANS near the wall and LES far away from you. This slide, I liked it. I suspect you may not like it, but I saw it once at a conference as well. A guy called Gavin Tabor in X, he's a professor in Exeter, but he basically drew kind of a map of turbulence modeling approaches to see how they're all related. So if this is turbulence, there's 3 fundamental ways to model it. DES, it's conceptually the easiest if it's the slowest to do. You just find out that here. Not quite, there's initial conditions is a thing. And then there's RANS approaches over here. And then we've LES over here. So within LES, how do you design those models, the mathematical formula, and that you're going to tune? There's algebraic ways and other ways to do that. For RANS, there's 2 main types of RANS. We're going to look at those. We're going to look at what's called the eddy viscosity model. This is the most common approach using the K epsilon. This is the most common type of RANS approach. But there's other types of eddy viscosity models, basically different formulas that you would use. And this K omega SST is kind of, if you don't know anything about turbulence, just use K omega SST. And then Reynolds stress is another variant, which is more accurate but more expensive. So there's these continuum. And then DES is a combination of LES and RANS, so you're kind of combining bits from here. So that's the main takeaway is the DNS, most expensive, most accurate, RANS, least expensive, least accurate, LES, somewhere in between. So for the rest of these slides, I'm just going to go through, well, how does RANS work? How is that derived? Because that's the one we're going to use in the assignment. And if you're going to do any turbulence, start with RANS first. And then if you really love this area, then you can learn more about how to extend it to LES and other approaches. So in this statistically steady flow, each variable, pressure, velocity, but also derived variables like stress, they can be decomposed into a time average value and a fluctuation about that value. So if I go back to my example over here, this is velocity at a point versus time. So we have a noisy signal like this. So I can say, well, this true velocity at that point, I can define that as u bar, which is just the average, a constant, plus u prime, which is a fluctuation away. So I can just say the value of anything, say velocity, I can just write that as a bar version, which is just the average in time, plus a fluctuation rate away. Yeah. So I can do that for any signal, even if it's not noisy. Where I'm going to define the average as this formula here. Let me just walk you through this. This is basically just saying calculate the area under the curve and then divide by the length. So I'll just give you the average. So this is just saying as we take the limit as t goes to infinity, we take a long enough time. That's the definition of our average. But it doesn't have to be applied to a time invariant flow. You can also have something that varies in time. So for example, if our velocity has a noise component, but there is like a smooth variation in time, then we can imagine that we've run this experiment, say, hundreds or thousands of times, and we always get a signal that looks like this, but the fluctuations are different, and we just average across all of those, and that would let us define what we call the ensemble average. So it's just a different perspective of it. So in that case, if we just n is the number of experiments, if we do thousands, millions, going to infinity experiments, then the value at each point in time is just the average across all your experiments. It's just a different perspective that lets this approach apply to transient problems. So it's like taking the average. It's basically trying to get rid of the noise, just like the average and plus the fluctuation. So to derive the RANS equations, I'm going to take my velocity and pressure in my Navier-Stokes, and I'm going to split them into mean and fluctuation. And then I'm going to see what happens to the equations. But before I do that, I just want to establish some rules of when I take averages of things, what happens. And to do that, I'm going to just use some MATLAB or Octave code so you can actually try this out. So let me explain what I'm actually doing. So I define a signal called phi. This could represent velocity. And phi is made up of an average part, phi bar, plus phi prime, which is a noise. So here's my phi prime I created, this red one here. This is just how I defined it. I just said there is a sine curve there, but I also added some random noise on top of it as well, just to make it somewhat random. Yeah, but just to have some different levels of frequency. So it's not just really high frequency noise, there's some lower frequency noise as well. And then I just say my phi bar is just the average here, the blue one is just 1. That's just the average velocity. So and then I say my true signal is just equal to the average plus the noise. So I've kind of created an artificial signal which has a constant average and a noise. So that's my yellow phi. Okay. So let me do some calculations on that. Let me print out, and if you're not familiar with MATLAB or Octave, that's fine. But what I'm doing is I'm taking phi, and I'm just saying write the mean, the average, the arithmetic average of that. So the mean of phi, I'm also get the mean of phi bar. Phi bar is just the constant one. And then also mean of phi prime, that's the noise. So if I do that for my, I think I just ran this for 1,000, which isn't actually that many points. So if I get the mean of phi, and that's the full signal, it's about 1. And if you increase n towards infinity, you'll see that it goes exactly to 1. If you take the mean of phi bar, that is just 1. If you take the mean of 1, it's going to be 1 as well. And if I take the mean of phi prime, the noise, that goes to 0. So the actual number I got with 1,000 isn't quite 0, but if you increase the number more and more and more, it goes towards 0. So, okay. Some maybe intuitive rules, but just to establish what they mean. So phi is made up of the phi bar, the average part, plus phi prime, the noise. So if I take the average, of my phi bar, so the mean or the average, that just gives back 1 in this case. So if I take my average of my signal, that is just the same as the average of the average, which is equal to 1. So if I just take the average of phi bar, that just gives me back the mean back, right? It gets rid of the noise. If I take the average of my noise, it's equal to 0. So if I average my full signal, the noise drops out, I just get the average of the mean value. And if I take the average of noise, that's equal to 0. Okay, so that's kind of maybe intuitive. So that's what I mean by these formulas. But there are some other expressions that are less intuitive. So if I take phi bar by phi bar, so it's the average, which is 1 multiplied by 1. I just multiply those signals to make the average. The average of that is 0. Or sorry, is just phi bar, is equal to 1. So the mean by itself, and if I take the mean squared and take the average, that's also just equal to 1. But maybe less intuitively is if I take phi prime by phi prime, this is the noise signal, and I multiply it by the noise signal, take the average of that, that is not 0. The mean of that is not 0. So if I take that noise signal and I multiply it by itself, that's essentially squaring the value. So sometimes they're negative, sometimes they're positive. But if I multiply by itself, that's squaring. So that means all those numbers have to be positive. So that one means I'll have noise that's always greater than 0. So the average of that is obviously going to be non-zero. It'll be the midpoint of that. So the average, the noise by itself, or the noise squared phi prime by phi prime, that no matter how many points I add, that never goes to 0. So that one makes sense when you think about it, but maybe it's not immediately obvious. If I multiply the average by the noise and take the average of all of that, then that does go to 0. If I get the average of the signal, the full signal, with the noise and average squared, and that doesn't go to 0, which makes sense. The offset is because of the phi prime by phi prime, like if you expanded that out. If you followed what I said there, I said the word average a lot. Okay, but the rules I can take away. Phi prime by itself squared, that means it'll be a positive number. It won't be about 0 anymore, so the average of that won't be 0. So that's not 0. If I multiply the average by prime average, that actually is 0. And the full signal by itself, average that, well, if I just expand it out in terms of average and prime, you'll see you get down to this term appears again. So that won't be 0. So the average of phi is equal to the mean value squared, but plus this other thing, which is non-zero. So now with those rules established, we'll go back to the Navier-Stokes equation, plug them in and see what happens. So this is our continuity equation. This is our velocity. I'm going to sub in the average plus the fluctuation. So I'm just plugging that in. And now I'm going to take the average of that equation. I'm going to average that equation in time or in an ensemble. So if I average across this gradient is just like it's a linear operator. So it means it's just like multiplying by a constant. So it's like A times this and A times that. So that means that we will have the average of this part plus the average of that. And we know the average of this just gives back this, the average of this is 0. So the continuity equation in Rand's form and Reynolds' average form is just exactly the same equation. It's just V now represents the average velocity, not the true velocity. So this is what we're going to solve for the average velocity. So that's simple. The complexity comes in a momentum equation. So we'll plug them in again. V, just V bar V prime, VV, so V bar V prime twice. Same for V here, and pressure, and then we have a pressure P bar. Average the whole equation. So like before, ddt is a linear operator, so the fluctuation drops out. Viscous stress term, the fluctuation drops out, we're just averaging it. Pressure term, the fluctuation drops out. So these three terms are exactly the same, we just put a bar over P. The problem is here, we have a squared, and this fluctuation by fluctuation squared appears. So our goal here was, we just want to rewrite the equations in terms of average velocity and average pressure. But unfortunately, we can't get rid of this fluctuation. And that fluctuation, we need to know the true flow to calculate that, which we don't know. So this thing here, and this is a good place to end, people normally bring this thing here, the divergence of this, to the right-hand side. That fluctuation by fluctuation average, people call that the Reynolds stress. So it has an effect on the flow, kind of like a stress. So conceptually, if you're trying to calculate the average flow quantities, they are affected by these very small scale fluctuations. So turbulence modeling, the whole area is just how can we calculate this thing without doing DNS? That's essentially it. So we'll talk of one approach to do that using K epsilon that you use in the lab, but I'll leave that to the next step. Okay, thanks.